Welcome to WikiPodcast. If you've ever imagined particles passing through solid walls, maybe, or existing in multiple places at the exact same time, well, you've dipped your toe into the seriously mind-bending world of quantum mechanics.
Hmm. And these aren't just concepts from science fiction, are they?
Not at all. They're actually at the very heart of our universe, and they're what we're exploring today. In this deep dive, part of our physics series focusing on modern physics, we're taking a closer look at some really fascinating insights.
Right. Our mission today is to pull out the most surprising facts, the crucial knowledge about two of the most, let's say, counterintuitive quantum phenomena, quantum tunneling and superposition.
Yeah, we're calling this one quantum tunneling and superposition, defying logic. Because, well, they really do seem to defy logic.
They certainly do. So today we're going to unpack these seemingly illogical concepts. We'll look at their history, understand them a bit better, and, crucially, discover how they profoundly impact, well, everything.
Everything. Like what?
Like the smallest electronics in your pocket, the biggest stars burning in the sky, maybe even the very fabric of life itself.
Okay, that's a huge scope. So how are we going to tackle this?
Well, we'll start by defining what quantum tunneling really means, touch on superposition too, then maybe trace their journey, from prediction to acceptance.
And then dive into the real world stuff, the applications.
Exactly. Astonishing applications and even some ongoing debates surrounding them. Let's start with just trying to grasp this unbelievable reality.
Okay, let's begin with quantum tunneling. To understand how weird this is, let's use an analogy. Imagine you're rolling a ball up a hill.
Right. Standard classical physics.
Exactly. If that ball doesn't have enough energy to get over the top, what happens?
It just rolls back down. End of story.
It cannot, under any circumstances, get to the other side. That's just common sense, right? The physics we see every day.
Precisely. But here's where quantum mechanics throws a curveball. In the quantum world, a particle, think an electron, approaching that same hill, that barrier, can, with a small but very real probability.
It can what?
It can tunnel right through the hill, appear on the other side, even without having enough energy to actually climb over it.
It just pops through the solid barrier. How?
It sounds like magic, I know. But it's a direct consequence of something fundamental, the wave nature of matter.
So particles aren't just tiny balls, they're also waves.
Exactly. They're described by wave functions. Think of it less like a solid point and more like a spread out ripple, or maybe a cloud of probability.
A probability cloud.
Right. And that wave function, mathematically, allows for a tiny, non-zero probability that the particle exists inside the barrier, and even on the other side.
So it's not skipping it, the wave sort of extends through it.
That's a good way to put it. The probability of this happening, of the wave function penetrating, and the particle appearing on the other side, it decreases exponentially based on a few things.
Okay, like what?
The barrier's height, how high the hill is, its width, how thick the hill is, and, importantly, the mass of the tunneling particle.
So if a particle is lighter and the barrier is thinner?
Bingo. It has a much better chance of tunneling. That's why you see this effect most prominently with very light particles, like electrons or protons.
And the barriers have to be incredibly thin, right?
Oh, absolutely tiny. For electrons, we're talking about thicknesses around 1 to 3 nanometers, maybe even smaller.
A nanometer is a billionth of a meter. That's almost nothing.
It's incredibly small. And for heavier particles, like protons, the barriers need to be even thinner, maybe around 0.1 nanometers. It really emphasizes that this is a quantum scale phenomena.
It really does. And you mentioned superposition earlier. While we're focusing on tunneling, maybe just a quick word on that. It sounds similarly strange.
Absolutely. Superposition is another one of those core quantum ideas that just breaks our everyday intuition. It basically says a particle can exist in multiple states, like being in multiple places at the same time.
At the same time.
Yep. Until you measure it anyway. Then it sort of chooses one state. Both tunneling and superposition really force you to accept that the quantum world operates under entirely different rules.
It makes you question, what being somewhere even means at that level. These ideas must have been, well, revolutionary when first proposed. Was it one person's discovery?
Not really a single eureka moment. It unfolded over time. The crucial groundwork was laid in 1926 with Erwin Schrödinger's equation.
The Schrödinger equation. Okay, I've heard of that.
It's the fundamental equation that describes how these quantum wave functions behave and evolve. Its publication really gave physicists the mathematical tools to start exploring these weird possibilities.
And people started using it right away.
Oh yes, pretty quickly. In 1927, Friedrich Hund was the first to apply it to barrier penetration, looking at molecular spectra.
Okay.
But a really huge early success came just a year later, in 1928. George Gamow and then independently Ronald Gurney and Edward Condon.
What did they do?
They used this new quantum math to explain alpha radioactive decay. They showed mathematically how alpha particles could actually tunnel out of the atomic nucleus.
So they used tunneling to explain something scientists already knew happened but couldn't explain how.
Exactly. It was a major validation for the theory. It showed tunneling wasn't just a weird mathematical quirk. It explained a real, observed phenomenon that had puzzled people for years.
But that must have been a big deal. And when did the name tunnel effect actually stick?
The term started appearing in the early 1930s. Walter Schottky used a German version in 1931, and then Yakov Frankl used the English term tunnel effect in a textbook in 1932. So it caught on pretty fast once the concept was solidified.
And the story doesn't stop in the 30s. There have been major breakthroughs, even Nobel Prizes, right?
Absolutely. The mid-20th century saw huge progress. Think about Leo Esaki in 1957. He demonstrated electron tunneling in semiconductors, which led directly to the tunnel diode.
A practical device based on tunneling.
Right. Then Ivar Javer in 1960 showed tunneling in superconductors, which was crucial evidence for understanding superconductivity. And Brian Josephson in 1962 predicted the tunneling of paired electrons, Cooper pairs, between superconductors.
Wow, that's quite a trio.
It was. And their collective work on quantum tunneling in solids earned Esaki, Javer, and Josephson the Nobel Prize in Physics in 1973. It really cemented the importance of tunneling in solid-state physics.
A Nobel for something that still sounds like science fiction. And didn't tunneling lead to another Nobel later on, something about seeing atoms?
You're thinking of the scanning tunneling microscope, the STM, invented by Gerd Binnig and Heinrich Rohr in 1981.
Right. The STM, how does that use tunneling?
It's ingenious. It uses the quantum tunneling of electrons across a tiny gap between a sharp needle tip and a surface to essentially feel the surface at an atomic level. By measuring the tunneling current, they could create images of individual atoms.
Imaging individual atoms. That's incredible.
It truly revolutionized surface science. And yes, Binnig and Rohr got the Nobel Prize for it in 1986. It's a perfect example of harnessing a bizarre quantum effect to build a powerful tool.
Okay, so we've got the theory, the history. Let's talk impact. Where does this quantum weirdness actually show up in our world, maybe even in things we use every day?
Well, it's closer than you think.
Yeah.
Take the electronics in your pocket or on your desk. Quantum tunneling is actually a fundamental limit for how small we can make transistors and other microelectronic components.
A limit? How so?
Well, as components get smaller, the insulating layers get thinner. If they get too thin, we're talking thinner than about a nanometer or so, electrons can just tunnel right through them when they shouldn't.
Like leakage.
Exactly. Unwanted leakage current. It causes devices to draw more power, generate more heat. It's a major headache for engineers designing the latest, tiniest chips.
But wait, you said it was also used in electronics? That sounds contradictory.
It does, but it's true. That leakage isn't always bad. It's actually the fundamental mechanism used to program the floating gates in flash memory.
Flash memory, like in my phone. Or a USB stick.
Precisely. To write data to a flash memory cell, you intentionally force electrons to tunnel through a thin insulating layer onto a floating gate. To erase it, you make them tunnel back off. So tunneling is storing your photos, your apps, your files right now.
So it's both a problem and a solution. That's interesting.
It really is. And looking ahead, researchers are actively developing new types of transistors called tunnel field effect transistors, or TFATs.
TFATs?
Yeah, these devices intentionally use tunneling as their primary switching mechanism. The idea is they could operate at much lower voltages, maybe cutting power consumption by like a factor of 100. It could lead to vastly more efficient computers and gadgets.
Okay, that's the super small scale. What about the super large scale? You mentioned stars.
Right, the cosmos.
Yeah.
This answers a really fundamental question. How do stars actually burn? How does fusion happen in their cores?
I thought it was just immense heat and pressure.
It is incredibly hot and dense, yes. But based on classical physics, the temperatures inside stars like our sun are actually not quite high enough for atomic nuclei, like hydrogen protons, to overcome their mutual electrical repulsion and smash together to fuse.
They should just repel each other like magnets.
Pretty much.
Yeah.
Classically, they just don't have enough energy to get close enough. But quantum tunneling gives them away.
They tunnel through the repulsion barrier.
Exactly. Even though the chance of any single proton tunneling through is tiny, There are just so many protons packed so densely in a star's core that tunneling happens often enough to sustain nuclear fusion.
Wow. So without quantum tunneling.
Stars wouldn't shine, at least not the way they do. Fusion wouldn't happen at those temperatures. Tunneling is literally essential for powering stars and creating all the heavier elements in the universe.
That's mind-blowing. And you also mentioned radioactive decay earlier. That's tunneling too.
Yes, alpha decay specifically. The alpha particle is essentially trapped inside the nucleus by a potential barrier, and it tunnels its way out. This provides a steady energy source, which could be important, for example, in thinking about potential life in subsurface oceans on icy moons astrobiology.
Okay, back down from the cosmos. We touched on the STM, the scanning tunneling microscope. Can we unpack how it lets us see atoms a bit more?
Sure. Imagine bringing an incredibly sharp metal tip, maybe just a few atoms wide at its very end, extremely close to a conducting surface, like fractions of a nanometer close.
Okay, ridiculously close.
Right. Then you apply a small voltage between the tip and the surface. Electrons want to flow, but classically they can't jump the gap. But because the gap is so tiny, they can quantum tunnel across it.
Creating a current.
A tiny, measurable tunneling current. Now, the amazing part is that this current is extremely sensitive to the distance between the tip and the surface. If the tip moves over a single atom bump, the distance changes slightly and the current changes significantly.
So by scanning the tip across the surface and keeping the current constant by adjusting the tip's height, you can map out the bumps and dips.
Exactly. You build up a topographical map of the surface atom by atom. The precision is staggering down to maybe 0.001 nanometers vertically. That's like 1% of an atomic diameter.
It's like having quantum fingers reading atomic braille. Just incredible. And its reach goes even further into chemistry. Tunneling helps reactions happen that shouldn't.
That's right, especially at very low temperatures, like in the vast cold clouds of gas and dust between stars.
Interstellar clouds.
Yeah. Classically, there's just not enough energy for many chemical reactions to occur there. But quantum tunneling allows atoms, particularly light ones like hydrogen, to tunnel through reaction barriers even at near absolute zero temperatures.
Enabling molecules to form in space.
Precisely. Molecules like molecular hydrogen, H2, water ice, even formaldehyde, key ingredients for forming stars, planets, and maybe life. Tunneling helps build them in these frigid environments where classical chemistry would stall.
And it affects reaction speeds, too. Something about isotope.
Yes, the kinetic isotope effect. If you replace an atom in a molecule with a heavier isotope, say, deuterium, instead of regular hydrogen, the reaction rate can sometimes change dramatically, more than classical models predict.
Because the heavier isotope tunnels less easily?
Exactly. It shows up particularly when hydrogen tunneling is a key step in the reaction mechanism. It's another way tunneling reveals itself in chemical processes.
Okay, this next one feels like the biggest leap. Quantum tunneling in biology. In living systems. How?
It's truly fascinating, and it's becoming increasingly recognized as a crucial, non-trivial quantum effect in life.
Non-trivial, meaning it actually makes a difference.
A significant difference. Think about the most basic processes of life. Energy transfer. Electron tunneling is key in many biochemical redox reactions, like photosynthesis, how plants capture light energy, and cellular respiration, how you convert food into usable energy in your cells. Tunneling allows electrons to move efficiently across biological distances in these processes. It's also involved in how many enzymes work, speeding up reactions.
So the very flow of energy in life relies on tunneling. That's amazing. But you also mentioned DNA.
Ah, yes. This is perhaps the most startling idea.
Yeah.
Proton tunneling and DNA mutations.
Protons tunneling inside our DNA.
It's a theoretical possibility, but a compelling one, proposed decades ago by Perl-Loudon. You know how DNA base pairs, like AT and GC, are held together by hydrogen bonds?
Right.
Well, within that hydrogen bond, the proton isn't just fixed in one spot. There's sort of an energy landscape with two wells or stable positions, separated by a small energy barrier. Normally, the proton sits in the deeper well.
Okay.
But quantum mechanics allows that proton to tunnel through the barrier into the other, less stable well. This is called a tautomeric transition. It changes the bonding properties slightly.
And if the DNA copies itself while the proton is in the wrong place?
Exactly. If DNA replication happens during that brief moment the proton is tunneled, it can cause the wrong base to be inserted into the new DNA strand, a point mutation.
A spontaneous mutation caused by quantum tunneling.
That's the idea. It suggests that this purely quantum effect could be a fundamental source of genetic variation and might even play a role in processes like aging or the development of cancer over time. It's still an active area of research, but it's a profound link between the quantum world and the core of biology.
That is genuinely mind-bending. Quantum physics potentially rewriting our genetic code.
Okay, but like all things quantum, it's not without its controversies and deeper puzzles, right? What about those claims of faster-than-light tunneling?
Ah, yes, the FTL tunneling debate. That's definitely stirred things up over the years. Some experiments and theoretical calculations seem to suggest that the peak of a particle's wave packet could appear on the far side of a barrier so quickly that its effective speed would be faster than light.
Faster than C. That would break, well, pretty much everything we know about causality, wouldn't it? It certainly appears to. If something travels faster than light, you could run into scenarios where effects happen before their causes in some reference frames. It's a big problem for physics.
So, is it real? Are particles breaking the cosmic speed limit?
The overwhelming consensus among physicists now is probably not. Or rather, the interpretation is tricky.
How so?
Most argue that the speed being measured in those experiments, often the group velocity, the speed of the wave packet's peak, doesn't actually represent the speed at which information, or the particle itself in a meaningful causal sense, is traveling.
So it's a mathematical artifact, maybe?
Something like that. Other parts of the wave packet arrive later, and careful analysis using relativistic quantum mechanics, like the Dirac equation, suggests that the actual propagation of any signal or causal influence remains strictly below the speed of light. Causality seems safe.
Okay, that's reassuring. Are there other, maybe less controversial advanced tunneling concepts?
Oh, definitely. There's a fascinating area called dynamical tunneling.
Dynamical tunneling, what's different about that?
In standard tunneling, you have a physical potential energy barrier, like our hill. In dynamical tunneling, quantum transport can happen between two distinct regions of phase-space think position and momentum that are classically separated, even if there's no obvious energy barrier in space between them.
So particles can jump between different types of motion even if classically they shouldn't be able to switch?
Kind of, yeah. It often involves systems that exhibit chaotic behavior classically. You hear terms like chaos-assisted tunneling or resonance-assisted tunneling. It shows that the concept of tunneling is even broader and more subtle than just penetrating simple barriers.
It just keeps getting weirder. But you mentioned earlier that the math behind tunneling isn't entirely unique. It relates to other waves.
That's a really important point. The mathematical equations describing quantum tunneling, how the wave function decays exponentially inside the barrier, are very similar to equations describing other wave phenomena.
Like what?
Like evanescent waves in optics, where light penetrates slightly into a medium where it shouldn't be able to propagate classically, or even waves on a string encountering a denser section.
So this weird quantum behavior follows rules that also apply to light, or even sound waves in some sense.
In a mathematical sense, yes. It highlights that wave behavior has these fundamental properties, whether it's a quantum probability wave or a classical electromagnetic wave. The quantum weirdness comes from applying wave mechanics to matter itself.
Okay, so wrapping this up. From particles seemingly defying solid walls to potentially causing DNA mutations, powering stars, and enabling us to see atoms, quantum tunneling, along with superposition, really paints a picture of reality that's profoundly different from our everyday intuition.
Absolutely. These aren't just abstract ideas for physicists anymore. They are active, real phenomena shaping our universe, driving cosmic processes, enabling modern technology, and maybe even influencing life itself.
This whole deep dive really makes you wonder, doesn't it? What other everyday things might have these hidden quantum explanations just, well, tunneling beneath the surface of our classical understanding?
It's a fantastic question. The more we look, the more connections we seem to find between the quantum and macroscopic worlds. There's likely still so much more to uncover.
Thanks for listening. Write us your opinion in the comments on what application of quantum tunneling do you find most surprising, or maybe what future technology do you think it could enable? Subscribe to the channel to help more listeners reach our episodes. Thank you, and have an amazing day.